also you have to accommodate that amount of heat that's lost from the sensor. Right? So what that means is that if you have a sensor that behaves with the hysteresis group, you have to take care of these few factors. Let's have a look at the repeatability. You would have heard, normally in spec sheet, you don't write much about repeatability. Just in case if you see that, repeatability just means that if you take that sensor, you do two measurements at different locations, they should give you the same value. If it's not the same value, if it differs a bit, that means it has some repeatability issue. Right? It's not that repeatable. So repeatability of the sensor will be limited by the hysteresis group and the noise that exists in the sensor. So if you have noise or if you have hysteresis, definitely you can't get back the same value at a different time. So another definition, output resolution, we'll be looking more into this. Is the ability of a sensor to distinguish between output values that are close together. What does that mean? You have two things in this resolution. We'll be looking at the output and input resolution. Actually, if I have the other slides together with this, it's easier to see. So now we have this. This is your nonlinear static response. Right? The static response here again means that it doesn't change at any point of time. It's static response. If it changes over time, you may experience drift. Right? So that one we call a dynamic response curve. So for a static response curve, the output resolution, for example, in this case, this one will be your output. So this amount of resolution, meaning the smallest amount that you can differentiate when there is a change. So if you look at the voltmeter, right now I took it to 200 millivolts, and I could see the value that's displayed over here, 0.00.0 for a 200 millivolts setting. 0.0. That means the resolution for this is up to 0.1. For anything that's 0.01, it couldn't differentiate. 0.02, it couldn't differentiate. Because its resolution is up to 0.1. That means if there's a change of 0.1, this thing can sense it. So its resolution value is that. So in this case, this sensor over here is quite small, but the value is about 0.1 for the output. This is what we call the output resolution. On the input side, you have certain resolution as well. This one is about 0.2. Right, if you read that scale over here, it's about 0.2. And this is what we call the input resolution. That small bit of change that can be differentiated. If the change is too small, then you couldn't differentiate. So that is your resolution. And this one, output resolution. And we have seen that the width for this, for the input width and output width respectively, is this part over here. Right? From this point, that point, that is your input width. And from this point, that is your output width. So if you take this ratio, the ratio of, say, if I start with the input side, taking the ratio of the input width divided by the input resolution. So I can form up an equation for that. My input width divided by input resolution. Or in the case of this, we have seen before that this one we call it x min, and this one over here we call it x max. So x max minus x min divided by input resolution. Now this ratio has a certain meaning. This is what we call the input dynamic range. So these are just terms here, definitions. So if you were to be asked, what is input dynamic range of certain sensor, even with certain value, and you would know that you need to take the input width divided by the input resolution. So the same goes for the other one. If you are looking at output dynamic range, that's equal to your output width divided by output resolution. And we have seen before, this one is your D max, that one is your D min or output. So that will be equal to D max minus D min divided by output resolution. Okay. Some definitions over here: the output dynamic range and the input dynamic range. Another thing in your spec sheet that you get to see a lot, and seriously a lot, that is sensitivity. So you have heard about accuracy, you have heard about resolution, and how about this thing that's called sensitivity? How sensitive is that equipment? How do we see that? Sensitivity has a formula. It's output width divided by input width. So if you take for example, this case, right? This is your input width, and that is your output width. So taking the output width divided by your input width, that is the definition for sensitivity. Yeah. But what does it mean? We're going to start by having two cases. Or actually, next year I should erase this. I already told you that which one is sensitive. But anyway, I have two curves over here, or two lines over here. One is called a low sensitivity, one is called a high sensitivity. Now, how do I come to that? I'll be taking some of these values over here. So, say for example, in this case, this one, I have this value here as maybe about 3 or so. This value over here is close to 10, or this case is 10. So the difference between these two values would be 10 minus 3 equal to 7. That's for this line over here that I'm taking. But this one over here, what I'm going to do is to take from this point to that point on the x-axis here for the sensor input. So roughly this is maybe about 4, this one maybe about 1, so 4 minus 1 equals 3. So if I were to use that sensitivity equation, sensitivity of this will be equal to my output width divided by my input width. And rightfully, I should take the whole width because it's a linear response, so I can just take part of it, no problem. You will still end up with the same ratio. If you take the smaller part of it, or the whole width itself, you still end up with the same gradient. So the sensitivity is kind of measurement of a gradient. So the output width, in my case here, would be 1.5. Come out over here. This one would be about 1.5. Yeah, I would say it's kind of like close to 1 is a little bit over 2. So the value over there is 1.5. So that's my output width, 1.5. Divided by the input width, that will be 3. And that's equal to 0.5. That's my sensitivity value. For this one, I'll take the output width again, that is 1.5, and divide by the input width, that is 7, and I get approximately about 0.214. So now here comes. This sensitivity value is higher compared to this sensitivity value. If you have a higher sensitivity value, that means it's more sensitive. Okay? If you have a lower sensitivity value, that means that device is not so sensitive. So these two lines over there will tell you which one is more sensitive and which one is less sensitive. Generally, the one with a steeper gradient, that one will tell you that it's more sensitive. But how do we measure this intuitively? Because we know that sensitivity is about output width divided by input width. So, in order to be a very sensitive instrument, that means in order for sensitivity to be very high, which one got to be a smaller value? Is it output width or input width? Input width. Right. It's only with a small denominator that your sensitivity will be very high. So now if you step back and think about it, I have input and then output. If the amount of input that I want to put in is just very little and corresponds to a lot of output, that means my instrument is quite sensitive. Right. I don't need to put in, I do not need to put in a lot of inputs before I can see appreciable output. So if you have an instrument that can behave this way, with a little bit of input width corresponds to a lot of output width, that means this instrument can be used to measure quite sensitively. So that's the definition for high sensitivity, when you have small input width. For low sensitivity, you will have larger input width. The next slide sort of like repeat the same thing when you have this low sensitivity part. So the output is going to be the same. And this one say, I think I did a measurement, it's about 3.3. This one is about 0.3. So the one with a lower input range or input width will give you a higher sensitivity. So high sensitivity gives good or fine input resolution. And conversely, low sensitivity gives a poor and coarse input resolution. There's another one that is the calibration. You would have heard a lot about calibration in your when you deal with a sensor. Some instruments, they need to be calibrated first. And if you're wondering what is it that's being calibrated, this is what it is. The calibration would determine an approximation for the static response curve. So we have this static response curve over here, right? That one is in black. This is what we want. But when we received the sensor, it actually didn't behave to this response, this static response curve that we want. Rather, it has this yellow one over here, that yellow line. And that yellow line is what we call our static calibration curve. We need to know that one before we would know what is our static response curve. This is what we will actually experience, and we will try to understand what are those values so that we can, from this point, get to that point. Right? So this point here, say it's about 2.3, and this point over here is about 1.9. So that amount, 2.3 minus 1.9, that is 0.4. That's an amount of correction that you need to do in order to calibrate your instrument. So that yellow line there is called a static response, static calibration curve. So what are the things that cause this static calibration curve to be at that position? There are a few things. One is drift, hysteresis, noise. They all are, they will all contribute to the uncertainty of your instrument. So it's important to know them so that you can then calibrate your instrument to behave as a static response curve. So let's do an example for this static calibration curve. There's this part here that is the error. So you can see that again you have the static response curve and then the static calibration curve. Static calibration curve would be this one over here, the one that's dark. That's your static calibration curve. So in between them, on the x-axis or the sensor input, this one is about 6.5. That one is about 6.2. So this is the amount that we call our is an amount that we need in order to calibrate it back to the static response curve. So this part here is what we call our input error. So there will be input error, and then there will be correspondingly the output error. And with that understanding of the error, we can then calibrate it back to the static response curve. What you have over here is actually a non-linear line, and what I thought is something that I included that's a little bit different from classical notes. This part here to show you that if you have the static response curve that is linear. If it is linear, what that means is that your error throughout will all be the same. This amount of error will be all the same. If it is non-linear, then the amount of error will vary across different parts of your input values. So it's actually easier to calibrate the linear response curve rather than the non-linear response curve, because if it is non-linear, it tends to be that your error will vary at different parts of the curve. I use the word curve loosely, sometimes to address it like a non-linear curve. Sometimes, even for a straight line, I also use the word curve. I just use that loosely. I'm not sure if you have this part in your notes. Do you have this part in your notes? Yeah, great. There's another part about nonlinearity errors. Some of you may be wondering, we seem to be talking a lot about this nonlinear response. This curve over here is nonlinear response. Why don't we correct that nonlinear response to a linear response? Can we do that? Yes, we can do that. But you would know that that correction varies along along the way. It's not always the same amount of correction because, for example, you want from this point to this point to correct it. So this line, this old line over here is the original one. You want to correct it to a linear response. So whenever it's at 8, the value of 8, you would take that y value and then reduce it by 17.9% in order to bring it to here. Right? So you're correcting it, reducing it to by 17.9%. So if you look at another value, let's say 6 over here, that will be the amount of change. Let's say this change, I didn't calculate that, let's say it's 2%. So if you want that nonlinear line to come back to a linear response, so at the value 6, you need to correct that output to increase it by 2%. So you can see that along the way, there's different percentages of change that needs to be applied. Sometimes this is seen to be a laborious task because then you need to be able to understand what is the drift that will come in, hysteresis that will come in, all of which it will affect how this nonlinear line is going to be applied. So if you have no choice but to use a sensor that has a nonlinear response, then you would need to do some correction to bring it back to a linear response. And the question is asked is that why can't we just live with a nonlinear response? I seem to know how it behaves. Why can't I just live with that? Now the reason is because it's just like if you've driven a car before, when you step on the acceleration, I'm not sure did you discover that that acceleration, the amount that you press down for acceleration is not going to be a linear response. Had it been a linear response, that means you actually need to push down the accelerator a lot more. So there are certain cases that does not require a linear response. You can live with a non-linear response because if you want to go faster, you actually just need to press a little bit more. Compared to initially, when you press it a lot more. So certain cars, they would design it maybe a linear response. Certain cars design it slightly non-linear response. Care for because it's harder to use our foot to control. Right? Because your foot, when it's down at the car beside the accelerator, is angled. Right? The amount of swing that you need when the foot is angled, that amount of swing is different from when it's straight and you swing. Right? So there's some study in understanding this to come up with the kind of response that's suitable for human beings to accelerate linearly. The output of it is that we get a sense that it's accelerating linearly, but then it's catering for how it is swinging for that angle. There is this term over here for sensor nonlinearity in terms of error that arises when an affine calibration curve is used to approximate a non-affine response curve. So what does this mean? It means preserving the parallel relationship. So the amount of error that will arise when we want to preserve this parallel relationship, this linear relationship over here. Now a lot of these graphs, they are taken from this reference. So I look it up online. You can actually find that this article from this website, I think it's in your set of notes as well. So if you're interested, you can look it up. It's a PDF thing, and you get to see a lot of these graphs that are coming Now, before we go, I just want to show you a video clip. Since we're doing our core in robotics, and you actually don't get